and thanks everyone for joining. I'm very happy to be here today at Q2B sharing our use case discovery strategy and also the latest platform that we have launched. So this is the outline of the topics that I will discuss. First, I'm going to tell you about what is the approach of Moody's Analytics to finding use cases. We will see what are the current research areas, the use cases that we are currently actively exploring. I will then go into more detail into a concrete case study that we are doing with QERA. And I will finally show you a demo of this benchmarking platform that we have launched recently. So regarding our approach to finding use cases, we are not just looking at a concrete kind of technology, but we are trying to stay quantum paradigm and quantum hardware agnostic. So the mission of our team is to evaluate the technology out there and try to see if we can get some advantage more in the near term, but also more monitoring what can happen in the future. And this is why the first thing that I wanted to talk to you about is that whenever we think about the use case, we are not just talking about purely quantum, but we also have a very strong focus in understanding what are the things that we can do with the techniques that are called quantum inspired. So techniques that are inspired from the study of quantum physics, but that run in classical hardware. We're also looking at the quantum computing paradigm of using quantum as an analog machine. So for instance, some examples here are the work that we are doing that I will talk more about in the case study, which is quantum reservoir computing with neutral atoms, but also quantum annealing. And lastly, the more general kind of quantum computing, which is the digital quantum paradigm. So what is the approach of our team when it comes to finding use cases? We are a company in the business of risk analysis, and our mission is to enable decision makers to make better decisions based on data and analytics. This is why we solve many computationally expensive problems, and we want to make sure that we are providing the best insights possible. This means that we need to solve the problems in the most accurate way and with the best technology. So whenever there's a new technology, we need to monitor it and understand how it will apply to us and prepare so that whenever it's ready, we can leverage it and we know exactly where we want to apply it. So this is why we define ourselves as hardware agnostic, pragmatic. We are driven towards action, so that's why we have also included the word makers. And what we are looking for is not just to speed up any kind of computation or to do any kind of problem or to compute any metric more accurately, but we are talking to our internal teams to understand where are the current computational bottlenecks and also where we have a business need for an enhancement in the method that we use today. So this is why when we talk about useful quantum computations, that is a term that is very widely used today, we are talking about business advantage. So whenever cost, runtime, and accuracy improvements translate into a benefit to our business. And in terms of when we expect to be able to apply these kind of techniques, we are looking both at the short term and the long term. There have been a lot of talks to date about this topic. So as I said, we are looking at the quantum-inspired paradigm because these are the techniques for which the hardware is already out there, and therefore we classify them as more short-term. And they are a good alternative to deep learning because they are white boxes versus the black box approach of neural networks. In these devices, we're also trying to look at these kind of problems where error mitigation and a few thousands of qubits can already do something useful. And then we don't lose sight about the long term, thinking about how we can leverage fault-tolerant quantum devices once they are available. So talking about what are the use cases that we are currently actively working in. These are the ones that we have developed this year. So as you see, we are working in topics related to the model related to climate, the risk related to climate. So for example, the use case that I will explain today is a project that we are doing with QERA and is supported by a DARPA grant, and is a project around forecasting the intensity of hurricanes or tropical cyclones. We're also doing research in how quantum techniques, concretely quantum physics-informed neural networks, can help in the modeling of floods. We have some use cases that are more cross-area, like Bayesian inference that can be applied to different application areas. We're also doing some work with Rigetti computing that are in this conference about recession prediction. So we're trying to enhance the accuracy of models that predict what's the probability of a recession in 12 months from today, answering that question. And on the left part of the slide, you can see one of the internal use cases that we're working on. We're working with one of our operational units in a concrete instance of a hard constraint optimization problem. These problems are difficult because when you restrict the search space, then classical algorithms struggle to converge, and also because classical algorithms have a problem of getting stuck in local minimum. And we are comparing different techniques from the different paradigms that I talked about. So quantum annealing and tensor networks that are the more near-term ones. And in the future, we also expect to be able to benchmark QAOA. So this is a work in progress still, but after talking to all the teams of quants and experts working in the classical side of quantum computing, of risk analysis, we have defined the potential areas of problems that we see. Some are more business specific and others are more cross-functional. So here you have a list of the areas where we think there's potential, and this is our conclusion after 1.5 years. That is the age of the quantum team, of the areas where quantum will affect us. And now let me go a little bit deeper into the case study. So Moody's is not in the business of predicting natural disasters, but we are consumers of the data and forecasts that the main meteorological agencies in the world generate. And we use this data and forecast to generate and enhance hurricane risk models. So what is our role? Our role is to help the market quantify risk, and some use cases of these risk models that come from climate are analyzing what is the economic impact of such events. For instance, for insurance companies, it helps them establish an appropriate policy pricing. And there are many other decisions that happen in business that need to understand what is the kind of risk. Concretely, for the case of hurricanes, we need to understand two specific problems. The first one is to predict what is the intensity of the hurricane or a tropical cyclone during its journey. And the second one is estimating what is the distribution of errors of the current forecast that the meteorological agencies give us so that we can bias correct them. And how does the classical paradigm look like for these kind of problems, for the two problems that I mentioned? Well, the state-of-the-art classical techniques that we use is to represent these complex, the complex dynamics of these systems as partial differential equation systems. And then, since they are very complex, we cannot solve them. With mathematical methods that are exact, but we need to perform numerical simulations. And what is the problem with these systems? They very accurately represent the complexity, the complex dynamics of the phenomena that we want to study, but the problem is that sometimes when we want to perform these numerical simulations, they can become too computationally expensive, especially if we are considering ensemble simulations. Ensemble simulations are a very similar concept to the ensemble methods that you may know from machine learning. It means that instead of performing only one simulation, you perform multiple simulations with different initial data, and then you look at the statistics. This is in an attempt to mitigate the errors that could come from only relying on a single simulation. But when we want to use this technique, it can become computationally prohibitive. What other things are happening in the classical domain? There have been advances in the latest years, as you all know, in the classical hardware side, and also we have been able to gather more data sets. So this is why machine learning has been proposed as a potential method for predicting the dynamics of these systems. But as you may have heard also in Deloitte's talk, sometimes the problem with these kind of methods is that they lack explainability. And therefore, but there is a certain class of machine learning algorithms that are reservoir computing, that is the case of reservoir computing, that are good at processing information generated by the dynamics of these complex systems, and they are good at processing the kind of data that come from these from the time series data that represent these dynamical systems. And they have very nice advantages compared to other methods in deep learning because they solve some of the usual problems that we see with neural networks. So for example, it helps with the ease of training, it helps with the processing speed, and power efficiency, system complexity, and it addresses some of the problems that come up when training neural networks with multiple layers, like recurrent neural networks that are the ones that are used in this case. Like, for example, the issues of the exploding or the vanishing gradients. So what are we attempting to answer with this research engagement that began in September? Our question is if these reservoir computing methods that are already promising in the area of doing forecasting and simulating the behavior of the dynamics of complex systems, we're trying to answer if we use quantum and quantum comes into the equation, whether this can help. And actually, we are collaborating with Q2B because their device with neutral atoms enables us to represent a very rich variety of systems, and therefore we are able to encode the dynamics of our systems in the neutral atoms. Then we let the system evolve according to the equation that that represents the dynamics of the system, and then we can measure and we can use the input of this quantum part as the input for a trainable classical linear regression. So the question that we are trying to answer is if quantum dynamics can provide new insights into the predictability of complex systems. And here, the data sources that we are dealing with are very diverse. So this is also an added complexity to the kind of problem that we are trying to solve. But you have to keep in mind that even if we have a lot of data about climate that can come from past events, or the data that we are gathering constantly from the satellite, or the physics-based models that theoretically tell us how the climate behaves. Still, the natural disasters are rare events. So we have a problem of data scarcity for these concrete natural disaster events. And the output of our research, we see 2 potential applications, and a third one that we have also revealed to DARPA, but is not public yet. So we expect that to have 2 use cases from the quantum reservoir model. The first one is to produce a model that could potentially be good at forecasting the intensity of hurricanes. And we would like to compare the output model that we get to the state-of-the-art models that are used, such as the one that we have written there. And the second use case is analyzing what is the distribution of the errors of the current models, so that we can use that information in order to bias correct the current ensemble prediction systems. And as I said, the first one is not specifically Moody's business, but since it is a use case that we foresee, we are also gonna study that and publish the results that we get, because we believe that that may be interesting for the field. And finally, I also mentioned in the description of my talk that we are doing benchmarking, because at this point, we cannot get advantage from quantum techniques, but what we can do is start to understand how it will benefit us. So this is why we have partnered with Multiverse Computing, that are experts in quantum algorithms, to develop this QF Studio platform. And the aim of this platform is to reduce the integration and preparation time, to make the quantum journey easier for our clients, and show what are the technological possibilities available without a high investment barrier. So we are going to put a problem marketplace of the problems that you see there, and this is how it's going to look like. Here are not exactly the same problems, because this is still the test environment. But basically, you will have a marketplace of problems. You can select a problem and learn about its description, what's the input and output data of its problem. And the good thing is that you can consume it via this graphical interface, but also via APIs, so to solve the problem of integration. And when you select a certain problem, you can basically add to it the different solvers that you want to benchmark against each other, and then all of these run in parallel. And once you get the results, you get a tool. Depending on the problem, the metrics that you compare will be different. But as a standard, you can see runtime, the total runtime, how much it costs. That it's also something that Scott Aronson mentioned this morning. This can be a reason to move from a technique to another, and the accuracy. The thing is that you will be able to access different hardware platforms, and also classical GPU resources in the cloud, and have these platforms so that you can see, like for the use cases that we mentioned, what is the best method for your concrete problem. Thank you so much.